You're welcome. Right, so the graph of x cubed over 3 looks something like that. Right. So notice it has positive slope everywhere. So we should expect a derivative graph that has positive y values everywhere, because the slopes on this graph become y values on our derivative graph. And then notice that this graph is concave down to the left of 0, and it's concave up to the right of 0. So we should expect the concavity on this graph to be the slopes on our derivative graph. Right? So where this has negative concavity, we should expect negative slope on the derivative. Where this has positive concavity, we should expect positive slope.
So it should change from negative to positive?
Yeah, it should change from negative slope to positive slope at 0 on our derivative graph. And our y values should be positive the whole time, because this graph has positive slope the whole time. So if you think about what the derivative of this is, it's x squared. Right? Because if I bring the 3 down to the front, the 3's would cancel out, and I'd get x squared. But what does x squared look like? Like this, right? It has negative slope, where this had negative y values. No, hold on, I'm confusing myself. This has positive y values, where this had positive slope. Right? This has positive slope everywhere, has positive y values everywhere. And then this is negative slope, where this was concave down, and it has positive slope, where this was concave up. Because the slopes on my derivative represent the concavity of my function, and the y's on my derivative represent the slopes of my function. So positive slope everywhere on your function means positive y values everywhere on your derivative. Does that kind of make sense a little bit?
What if it give you like the first derivative and you're looking for the second derivative?
Then, so if they ask you a question about the second derivative, like this problem that we're doing right here, the one that we were just doing, so when they ask you about the second derivative, they're asking you about the concavity of the function. That's what the second derivative represents. Well, the concavity of your function is the slope of the first derivative. So the second derivative is the slope of the first derivative.
So,
because derivative is always slope. So if you think about it, second derivative is the derivative of the derivative, right? Which is confusing, but it's a derivative, and it's the slope of whatever it's the derivative of. So like on this one that we were just doing, we were looking for where our original function would have a point of inflection. Have a point of inflection if your second derivative changes sign. Your second derivative is the slope of your first derivative. So we're looking for where the slope was changing sign. Alright. Okay, number 18. In the xy plane, the line x plus y equals k, where k is a constant, is tangent to the graph of y equals x squared plus 3x plus 1. What's the value of k? I know I've worked this before. I'll try to remember how to do it. Right, so first off, a tangent line, you would use the derivative to find the slope of the tangent line. So I'm going to go ahead and take the derivative of that, because I know the derivative might be involved somewhere. Because tangent, you should think derivative. Alright, so this is the slope of the tangent line. Okay, so if I solve this equation for y, I'll get y equals negative x plus k. And the slope of this line is negative 1. Right. So I know that that slope for that tangent line had to come from this expression. That's where the negative 1 would have come from. To get the slope of a tangent line, you take the derivative and you plug x into it. So they plugged something into this and got negative 1. Use that x that they, so if I do that, 2x plus 3 equals negative 1. Oh, negative 2. So they plug negative 2 into x. So negative 2 is the x coordinate of the point that of where the tangent touches that graph. These two have to be equal. 2x plus 3 and negative 1 have to be equal. This is the one that only like 22% of people got right. Less than half the people who got a 5 got this one right. This one's pretty tricky.
Oh, because you're looking for K.
Yes, because we're looking for K. So it's not negative 2. Right. So once you get negative 2, you're going to plug it into this equation to get y, because you need to know x and y to get k. You have to be able to add the x and the y together to get k. So once you know the x from this equation, then if you plug that in, you get 4 minus negative 2 plus 1, negative 1, so then you can add those together to get k. But the key is to remember that the slope of a tangent line comes from the derivative. So they gave you the tangent line, which you could tell the slope if you solved for y. That negative 1 had to come from the derivative. So then you get an equation to figure out, well, what did they plug into the derivative to get negative 1? And then once you had the x coordinate, you could plug back into the function to find the y coordinate, and then you could add them together. All right, 19. The reason they threw 19 out was calculus teachers to find horizontal asymptotes that you use Bobo, Botno, ECC, and then they put a question on here that you couldn't use Bobo, Botno, ECC on. So they threw it out because, like, I mean, even people that made, if they were to do this again, which I mean they could, what you would want to do to figure this out is plug in a really big positive number and a really big negative number and see what happens.
And this actually without calculator, right?
This is without a calculator, yeah. So if you think about plugging in a really big positive number, like 1,000. Right. 2 to the 1,000 is huge, right? And so adding 5 to 2 to the 1,000 doesn't really make a difference, right? 2 to the 1,000 is going to be such a large number that adding 5 doesn't really matter. So this is basically the same as 2 to the 1,000 on the top. Because plus 5, I mean, you know, you're talking about a billionaire getting 5/10 of a cent. Like, it doesn't matter. Same thing on the bottom. The 1 doesn't really affect anything. So on the bottom, you really have just this. So basically, the top and the bottom are the same, except they have different signs. So you would get about negative 1. Now, if I plug in a really big negative number, now this is really small. 2 to the negative 1,000 would be 1 over 2 to the 1,000. It would be like dividing 1 by a really big number. So this gets really small, right? This gets really big, making this not matter. This gets really small. When you have a really big a really big negative exponent, actually makes this really small, which makes this part not matter. Right? The 2 to the 1,000 really making them negligible. So we basically get 5 over 1, which is 5. Right. Hopefully there aren't going to be that, but they could. They did it that year. I think it was kind of like a little slap on the wrist.
Wait, how do you think the little button?
Because you don't have powers of x. X is the power. Bobo button only works if you have like x to a power.
You only use Bobo Botno ECC when it's approaching infinity or
Or for horizontal asymptotes, yeah. Yeah, because that's what horizontal asymptote is it's what's happening as x gets big, or x gets small, which is what a limit at infinity is. Right. Okay. Number 20, let f be a function with a second derivative given by, what are the x coordinates of the points of inflection? So they gave you the second derivative. So remember, to find points of inflection, you're looking for where the second derivative is 0 or undefined and changes sign. So they gave you the second derivative. You can tell that it equals 0 anywhere that one of its factors equals 0. Right, so that would be at 0, 3, and 6. At 0, 3, and 6, the second derivative equals 0. So this is where we make the little sign chart to see if it changes signs at this point. Right? Plug into the second derivative. So if I plug like -1 in, I'm going to get 1 times -4 times -7. That's a positive. If I plug in 1, I'm going to get 1 times -2 times -5. That's a positive. 4, I'm going to get 16 times 1 times -2. And 7, I'm going to get 49 times 4 times 1. So the only two places where it actually changes signs are at 3 and 6. Right. If it would change with x to the 4th, it wouldn't. Right. So it would change signs. Well, I put my 3, right, the 3 places where this equals 0. The second derivative equals 0 at 0, 3, and 6.
Wait, how would you
So I
have
put
that?
those on there.
How about making all of these equal?
Yeah, by setting each of the factors equal to 0.
So this is where you like bring in the
Yeah.
right?
Yeah. These are where the second derivative equals 0. So I just chose test points, right, around those numbers. I know y'all's brains are getting bogged down. All right. All right, let's see.
No, English tomorrow, Thursday is yeah.
I don't think English is gonna be like.
Okay, so let's look. This is kind of like the graph one. So let's see. No, I can get this one. So constant. A particle moves along a straight line. The graph of the particle's position is shown above. So this is S. So everything is as it should be. Y is Y, slope is slope, concavity is concavity. The graph has horizontal tangents at 1 and 5 and a pointed inflection at 2. So that means it's concave up to the left and down to the right. For what values of t is the velocity of the particle increasing? The velocity is the derivative of position. Right, so it's the slope. So basically, where's the slope positive? Wait, what? Which number is this? Oh, no. Yeah, no. Where the velocity, not where the velocity is positive, where the velocity is increasing. Where the velocity is increasing. So where the slope of the velocity is positive. Yes, so where it's concave up. Sorry, see my brain's even getting fried between reviewing y'all and reviewing my algebra kids. I'm like so testing you out. Alright, so it doesn't say where is the velocity positive. It says where is the velocity increasing. So basically, where is the slope increasing? Well, what makes a graph concave up is its slope is increasing. And what makes it concave down is its slope is decreasing. So basically, they're asking you where the acceleration is positive. Velocity is increasing if acceleration is positive. And acceleration would be the concavity of this graph. So, diverging. This is number what, 21? Only 22% of people got this one right.
Wait, I don't get it. I don't know.
Huh? Yes. I would put this is where is the velocity, right? This is where the position is, right? Because increasing where velocity is positive. This is asking where the velocity is increasing. That's why only 22% of people got it right, because I guarantee they did the same thing that I just did. They misread the problem. It doesn't say where is position increasing. It doesn't say where is velocity positive. It says where is velocity increasing. So where is the slope of velocity? Slope of velocity would be the second derivative of position, the concavity.
So where is the concavity now?
Yes. That one
You
was
know,
harder
it's
than I
interesting.
expected it to be. I thought it would be
I think
pure compliment.